Hello everyone, welcome to the second lecture on molecular dynamics. Today we're going to talk about potential energy and force fields. In our last lecture we have seen that this is the velocity-Berlet algorithm, which is the solution of the classical equations of motion, where we can compute the coordinates at a particular time step t plus delta t from the coordinates of a previous time step, and also we can compute the velocities of the current time step from the velocities of the previous time step. Also, we need to know the gradient of the potential energy here and also here in order to solve these two equations. This potential energy gradient can be computed in three different ways. The first way is to use a classical force field, and where we will have a very simple equation which relates the potential energy with the coordinates of our system. If we use a force field, then we are running a classical molecular dynamics simulation. Also, we can solve the Schrödinger equation in order to get the potential energy, and if this is the case, then we are running ab initio molecular dynamics. And finally, we can also combine both approximations by solving the Schrödinger equation for a small fragment of the system, so we use quantum mechanics for a small fragment of the system, and we use a molecular mechanics force field for the rest of the system, for the environment. This approach is usually called QM-MM molecular dynamics. In this lecture, we are going to focus on the first approximation, which is the most common one, where we are going to use a force field in order to compute the gradient of the potential energy to solve the velocity-Berlet equations. But before explaining in more detail the force fields, let me say a few words about the potential energy. Usually we want to compute the potential energy of our system because it will dictate the behavior of the system, so it will tell us how the dynamics of our system is. Usually we can define the potential energy as the interaction energy among all particles of our system, electrons and nuclei. For example, let's say we have an atom A, which is formed by positively charged nuclei and also by negatively charged electrons, represented here in blue and in red respectively. And now we have a second atom B, also with a positive nucleus and also some electrons in red. So the potential energy is the interaction between nucleus of atom A and nucleus of atom B. Now we also have electron-electron interactions and electron-nucleus interactions. So the interactions between nuclei and between electrons is repulsive, so we will have a positive potential energy, and the interaction between the electrons and the nuclei is attractive, so our potential energy will be negative. So if we represent the potential energy, that means the interaction energy between the atoms A and B against the separation between both atoms, we will have this potential energy shape, where at very long distance there is no interaction, so the potential energy is equal to 0. Now at very short distances, the repulsion between the electrons will dominate, so we will have repulsion, so we will have a potential energy which is positive, and at intermediate distances attraction will dominate. So we will have here our minimum in the potential energy curve. So the equilibrium distance for the molecule will be around this region. So it's very relevant to know the shape of the potential energy surface because, as we said, it will dictate the behavior of the system. For example, let's say we have two diatomic molecules. The first molecule, AB, has this potential energy curve, so the curvature is relatively small. So that means if we represent the vibration of the diatomic molecule as a particle running in this potential energy surface, so we will have this kind of vibration. So since the curvature of our potential energy is not high, so the vibration is relatively slow. However, if we have a second molecule, CD, whose potential energy has a larger curvature, now the vibration will be much faster, because the gradient here of the potential energy is very large. So the acceleration of our classical particle running along this potential energy curve is higher. A second example, For example, we can have a process where we go from the species A to the species B, and this is the potential energy surface. We have here our minimum for the reactance A and the minimum for the reactance B, and we have to overcome this energy barrier in order to go from A to B. So if this is the case, in this situation the energy barrier is relatively large, so our reaction will be slow, but we also have a positive reaction energy because the energy of the products is larger than the energy of the reactants. So that means the potential energy is positive, or in other words, the reaction is unfavorable from the thermodynamic point of view. Now, if we have a second reaction where we go from C to D, and this is the potential energy profile of our second reaction, in this case, the energy barrier is smaller than in the previous case. Here, remember, the energy barrier is relatively large. Now we have here a smaller energy barrier. So that means our reaction will be faster in this situation, in the reaction C to D. And now the potential energy when we go from C to D is negative. So the reaction will be favorable from the thermodynamic point of view. So as we can see here, if we know the shape of the potential energy surface, we can know a lot of information about the process we are investigating. So let's now explain how we can compute the potential energy of our system using a force field. So a force field is a simple equation which relates the potential energy of our system with its internal coordinates. So we will have a simple equation which relates the potential energy with bond distances, bond angles, dihedral angles, and so on. So we will try to have a relation between potential energy and internal coordinates. In most of the force fields, the potential energy is split into bonded and non-bonded interactions. For example, let's focus on this molecule, on the benzoic acid. So the total potential energy can be written as bonded interactions between atoms which are directly bonded. So the separation between these two atoms is only one bond. We will call to this potential energy bond potential energy, and it's represented here in blue. We will have also interactions between atoms which are separated by two bonds. So here we will have the interaction, for example, between this hydrogen atom and this carbon atom, and the separation between these two atoms is only two bonds. Since these two bonds form an angle, we will call this potential energy the angle or the angular potential energy. We can also have interactions between atoms which are separated by three bonds. So here we are computed the interaction between this carbon atom and this oxygen atom, and the separation is 1, 2, and 3 bonds. Usually this term is called torsion potential or dihedral potential, which is the notation we use here, dihedral potential, because this potential energy will depend on the dihedral angle formed by this plane formed by the atom 1, 2, 3, and the plane formed by the atom 2, 3, and 4. But we will see this in more detail in a few slides. And finally, we also have a non-bonded interaction energy between atoms which are separated by more than 3 bonds. In that case, we have the interaction energy between this hydrogen atom and this hydrogen atom, and which are separated by 1, 2, 3, 4, 5 bonds. So the first 3 terms in this equation are called bonded interactions, and the last term is the non-bonded interactions. Now we are going to see in more detail each of these 4 terms of equation 3. So the first thing we need to know in order to use a force field is that we need to classify first the atoms of our molecule in atom types, because depending on the atom type we have in our molecule, we will have different interactions with the other atoms. So again, let's focus on the benzoic acid as example. So we will have, for example, bonded interactions between these 2 carbon atoms here, but also between these 2 carbon atoms. So generally speaking, we will have a potential energy term which will define the carbon-carbon interaction here, but also the carbon-carbon interaction here. So these 4 carbons, so this one, and these 2 aromatic carbons are clearly different. So even if we have a carbon-carbon interaction here and a carbon-carbon interaction here, these 2 interactions are clearly different. So we need to distinguish between these 2 situations. So this is why our first step is to classify the atoms of our molecule in atom types. For example, if we use the general Amber force field, we will have the following classification. In the general Amber force field, the carbon atoms which are part of aromatic systems are called Ca. This is an arbitrary name and this is an arbitrary classification, but we are going to use this classification in these slides. But of course, different force fields will have different classifications and also different parameters. In the general Amber force fields, the hydrogen atoms which are bonded to aromatic carbon atoms are called Ha. Now we also have sp2 carbons in carbonyl groups, like here, and they are called just C. We will also have an oxygen atom connected to one atom only, so the general Amber force field call this atom O. And finally, we will have also the OH and the HO group, which are the 2 atoms in the hydroxyl group according to the general Amber force field. Okay, so this is the classification of our atoms. So we have already our atom types. As I said, this is arbitrary. And now we need to know the parameters of for each atom type to compute the potential energy in our system. For example, the carbon atom Ca here will have different parameters than the carbon atom C here. And in this way, we will be able to distinguish between this carbon-carbon interaction and this carbon-carbon interaction. Okay, so now let's have a look at each of these potential energy terms in the equation 3. Okay, let's focus first on the bond and angle interaction. So we will focus on this kind of interactions between atoms which are directly bonded, and also the interactions between 2 atoms which are separated by two bonds. So in these 2 situations, we use usually harmonic potentials. So the potential energy of the bond will be 1/2 multiplied by a force constant and then the square of the separation minus the equilibrium distance between the atoms. So this is the typical equation for the harmonic oscillator. And here R is the separation between the 2 atoms. We want to compute the interaction energy. We will have a similar equation for the angle contribution, but now instead of distances, we will have an angle here. So theta will be the angle between hydrogen, carbon, and carbon, for example. Okay, so let's say this is the real potential energy of our system. For example, if we talk about the bond potential, here we will have a bond distance, and the potential energy has this shape, as we already know. Here, when the separation is large, the potential energy goes to 0 because we don't have interaction between the atoms. Okay, so our real potential energy shape is anharmonic, so that means we are using here a huge approximation because we are using harmonic potentials to model this situation, which is anharmonic. So that means our force field, so the force fields which use harmonic potentials are correct only close to the equilibrium distance. So close to the equilibrium distance and also close to the equilibrium angles. So in other words, if we run a simulation using harmonic potentials at very high temperatures, our simulation will not be correct because at high temperatures the vibrations will be, the amplitude of the vibrations will be very large, and we will deviate a lot from the equilibrium distance, and the harmonic potential will not be able to reproduce such a situation. Also, as you can imagine, harmonic potentials cannot describe bond breaking information because our potential energy increase to infinite with increasing the distance. That means we will never dissociate our molecule. So in summary, we can use only force fields based on harmonic potentials at standard temperatures, so we cannot run simulations at very high temperatures, and also we cannot describe chemical reactions. Okay, so the first thing we need to do is, now that we have our atom types, we can classify our bonds in bond types. For example, we will have Ca-Ca bonds, we will have Ca-Ha bonds, also we have here a C8-C bond, and so on. So we have in this molecule 6 different bond types, and now we can also classify the angle types. For example, we have Ca-Ca-Ca, this is one angle. We have also Ca-Ca-Ha, and we also have, for example, Ca-Ca-C, and so on. So we classify our bonds and our angles in bond types and angle types, and then each of these types will have different parameters. So for example, for the bonds, each bond type will have a different force constant here, a different Kb, and also a different equilibrium distance here. And the same for the angles. So each angle type will have a different force constant here and a different equilibrium value for the angle. Now let's focus on the third term in this equation, in equation 3. So we are going to focus on the torsion or dihedral potential. So remember this potential energy term represents the energy, the potential energy between atoms which are separated by 3 bonds. For example, this oxygen and this carbon atom. So in this for this kind of interactions, we usually use the Fourier equation, which is this one, equation number 6, where omega is the dihedral angle formed by the plane defined by the atoms 1, 2, 3, and the plane defined by the atoms 2, 3, 4. In other words, in our example, we will have a plane defined by the atom Ca, by the second atom Ca, and this atom C. So this is the first plane, Ca, Ca, C. And we will have a second plane which is defined by the atoms, Ca, C, O. So these two planes form an angle which in this case is 0, is very easy to see, and this angle is called the dihedral angle. In equation 6, the other parameters Kt, N, and gamma are the parameters of the force field which will define the shape of the torsion potential. Again, the first thing we need to do is classify our dihedral angles in torsion types, and then we will have different parameters for each of these torsion types. For example, let's have a look in detail to the potential at the potential of the ethane molecule. As you probably know, the ethane molecule has 3 potential energy minima with respect to the torsion of one of the methyl groups with respect to the other methyl group. For example, in this first minimum, the separation between these 2 hydrogen atoms is the largest possible, so the repulsion between these 2 hydrogens is small, and this is why we are in a minimum. However, if we rotate this methyl group 60 degrees, then we have this situation where one of the hydrogen is just in front of the other hydrogen, and the repulsion interaction is very large, so the potential energy increase. Then if we continue the rotation another 60 degrees, we have here a second minimum, then we have a second maximum, third minimum, and third maximum. So we have 3 minima and 3 maxima along the torsion of the ethane molecule. So in equation 6, which describes this torsion interaction, N will give us the number of minima. So for example, in the case of ethane, N will be equal to 3 because we have, as we said, 3 different minima. Then Kt is the energy barrier for going from one minima to the other. So in this example, the energy barrier will be 2.9 kilocalories per mole. And finally, the combination of gamma and n will provide the position of the minima and the maxima along this angle range. For example, if n is odd and gamma is 0, or if n is even and gamma is 180, then the minimum is located at 180 degrees, as in this example. This is probably a bit complicated to see, so the best thing you can do is to plot this equation, trying different values for n and gamma, and then you will figure out how the combination of n and gamma will provide you the position of the minima at different angles. Now let's have a look at the last term, the non-bonded potential term here in equation 3. So for example, this is the interaction between these two atoms, which, remember, are separated by more than 3 bonds. So usually non-bonded interactions have 3 potential components. We will have a Coulombic interaction, we will also have van der Waals interactions, and finally repulsion interactions. In this lecture, we are going to explain only what is called fixed charge force fields, where we only have these 3 contributions, and these force fields are called fixed charges because the charges of our atoms will be the same all the time. So in other words, even if we have 2 molecules interacting very strongly, we don't reproduce the polarizability of the molecules. If we want to have the polarizability included in our model, we need to use another different type of force fields, which are called polarizable force fields. But this will be the subject of a future lecture. For the moment, let's focus on the most simple force fields. So as I said, we have 3 different contributions. So for example, let's imagine we have these 2 atoms interacting, the atom I and the atom J. So each of the atoms will have a charge, and these 2 atoms will be separated by a particular distance r. So the first potential energy contribution we will have is the Coulombic interaction, or the electrostatic interaction, which is given by this equation. Here we have the product of the charges over the separation between the atoms. We can also have dipole-dipole interactions representing the van der Waals interactions, and as you probably know, the van der Waals interactions are always attractive, at least in solution. So this is why we have here a minus, and the potential energy change with the inverse of the 6th power of the distance. And finally, so that means we will have this potential energy curve here representing the van der Waals interactions. So at very long distances, the interaction is 0, and when we decrease the distance, the potential energy is more and more negative. So the attraction increases with decreasing the distance. But if the separation is very small, so if this separation here between the atoms is very, very small, then we will have repulsion between the electronic clouds of atom I and the electronic cloud of atom J. So we will have electron-electron repulsion. From a quantum mechanical point of view, this repulsion changes with exponential of the separation. But usually, from the computational point of view, the calculation of an exponential is relatively expensive. So usually we use a function which behaves very similar as an exponential, which is the inverse of the 12th power of the separation. So usually we use this potential shape to mimic the repulsion between electrons in our molecules. So we will have here this second contribution, which is repulsive at short distances and vanish at long separations. Okay, so in total this will be the potential energy shape, where we have our repulsive contribution and the attractive contribution. In order to mimic this situation, we usually use what is called the Lennard-Jones potential, which is this one, is equation 10 here. So as you can see here we have the repulsion term and we have here the attractive term. And sigma and epsilon in this equation has a kind of physical meaning. So sigma is the separation between the atoms where the potential energy is 0, and epsilon is the well of the potential. Usually we don't have sigma and epsilon for each pair of atoms, but we have individual epsilon and sigma for each atom type. And then if we know epsilon and sigma for each atom type, we can compute here the interacting sigma and the interacting epsilon as the arithmetic mean and the geometric mean respectively. And then we can compute the potential energy using these parameters. So remember that in our molecule we have different atom types. Each atom type will have a different epsilon and sigma. So we will have a different Lennard-Jones interaction for each pair of atoms I and J. Let's summarize what we have. So we are going to compute the bond interactions using a harmonic potential, which depends on the square of the separation between the atoms. We are going to use also a harmonic potential for the angle interactions, the Fourier equation for the dihedral interactions or torsion interactions, and finally for the non-bonded interactions we will have three different contributions. The first one is the electrostatic interaction between the charges in our system. Remember that if we use a point charge force field, we don't have polarization, which means that the charges of our atoms are always the same independently on the chemical environment. We also have the Lennard-Jones potential, which reproduces the repulsion between electrons, which is the first term here, and the van der Waals interactions, which is represented by the second term here. So now we have a relatively simple equation, equation 12, which relates the potential energy of our system with internal coordinates, or in other words, with the geometry. And finally, it is important to say that the parameters of our force field, so this K, the R0, the Ka, the θ0, Kt, and so on, all these parameters are chosen to reproduce experimental data or quantum mechanical calculations. Usually, we don't parameterize our force field, but we use force fields which were already parameterized for many years for many people, like the Amber force field or the Charm force field, which were parameterized for proteins, for DNA strands, for lipids, for water, for organic molecules, and so on. Remember that our goal was to obtain a simple equation which relates the potential energy with the coordinates, in that case with internal coordinates, because now we can compute very easily the gradient of the potential energy, which is the variation of the potential energy with the coordinates, and put it here in the velocity-Verlet equations in order to have the time evolution of coordinates and velocities. Thank you very much for watching, and see you in the next tutorial.